Oh, okay. So we are very Sanjay Reddy today for the speaker. And so let me introduce Sanjay. Of course, many of the audience already know who Sanjay is. And so Sanjay got the master degree in India Institute of Technology, and then moved to Stony Brook, and then got a PhD in 1998, and then he went to INT as a postdoc fellow, and then he moved to CTP, MIT, and Los Alamos as a staff scientist, and then came back to INT Seattle as a senior fellow, and also the professor of physics of University of Washington. And Sanjay is known for many interesting works about the neutron star and color superconductivity and dense nuclear matter and so on. And recently analyzing the gravitational waves and also the property of a neutron star constraint. And also he's known as one of the pioneers to apply the very exotic idea of cochronic matter to the equation of state of a neutron star. And so, well, the Sanjay is really covering the very wide range of physics related to dense nuclear matter and neutron star and astronuclear physics. Okay, so Sanjay, please start your talk.
Okay, thank you very much, Kenji, for that kind introduction. What I was hoping to do in the talk today was survey some interesting insights we have been able to derive by combining theory and observations relating to dense matter. A very large fraction of my talk will be focused on dense matter, and depending on how much time I have, I will say a few things about how neutron stars could help constrain dark matter, if dark matter is indeed a particle or a set of particles. So the plan of this talk is as follows. I will begin with a brief motivation and an introduction. I suspect that this group doesn't really need this, so I'll rush through that. And then the significant focus will be on appreciating what we've learned from mass and radius measurements of neutron stars and that what it tells us about the equation of state. And then I will have a few things to say about accreting neutron stars because they seem to be excellent probes of the thermal and transport properties. And then I will mention how things might change in the next generation gravitational wave era, and time permitting, say a few things about the dark side of neutron stars. Before I proceed, this is work that I've done, that I've been involved in over the past decade. It involves many collaborators, and a lot of what I'm about to tell you is based on stuff I learned through these collaborations. I want to especially highlight some of the young people, Christian Drischler, Sophia Hahn, Ingo Tews, and Tianqi Zhou. They're all made important contributions to what I'm about to say about neutron star structure and equation of state. And when it comes to accreting neutron stars, there are a lot of senior collaborators whose names you probably will recognize from the list here. But Andrew Cumming at McGill and Ed Brown at Michigan State played a critical role in analyzing accreting neutron stars, as did Danny Page from Mexico. And my interest in dark matter started through my collaborations with the late Ann Nelson, and some of the students that I've worked with at UW, including Ermal Rapai and Dake Zhou, both of them now at UC Berkeley. And data relating to gravitational waves and its analysis, I was helped by many people from the LIGO collaboration and people working with gravitational waves. And the young people there include Reed Essick and Colin Capano. So let me get started. Why are neutron stars interesting? Because I think we know neutron stars hold answers to some of the most interesting questions, especially for those of us interested in dense matter and matter under extreme conditions. We expect to learn something about the states of matter, perhaps even the composition of matter at extreme density through neutron star observations. Clearly, I will discuss some of it today. In addition, we understand that dense matter plays a critical role in various explosive phenomena, from core collapse supernovae to magnetar flares to neutron star mergers. And we've also appreciated the fact that the dynamics of neutron stars, especially during a merger, is intimately connected to the question of heavy element nucleosynthesis. And one of the great successes of understanding the electromagnetic signatures from the first neutron star merger event was the recognition that, in fact, neutron star mergers do have the right conditions to produce heavy elements. And finally, in recent years, many people have looked at how neutron star observations might constrain dark matter. To this audience, I thought I'd start with this slide because most of you work on the QCD phase diagram, understanding its properties in equilibrium and out of equilibrium. I wanted to bring to your attention some similarities between the finite temperature axis and the finite chemical potential axis of this phase diagram. Many of you are actively working to find a critical point in the phase diagram that would signal the existence of a first order phase transition at finite chemical potential. Let me begin by just moving along the axes before I get into the central regions of the QCD phase diagram. Along the temperature axis, where we have lattice QCD and heavy ion experiments and phenomenology, we've learned a great deal. We know that extremely low temperatures, we have a good description of the finite temperature phases, starting from chiral perturbation theory, the interactions of pions between themselves and heavier mesons. And at very high temperature, we have perturbative QCD. And in the middle, we have lattice QCD to tell us at least the equilibrium properties and maybe some transport properties, hints at some of the transport properties in the intervening temperatures. It's also remarkable that there seems to be a transition from pions and hadronic heavy resonances to some phase of matter which appears to be very strongly coupled. And this transition has really inspired some of the thinking even in understanding dense matter at low temperature. So if we think about the finite chemical potential diagram, through low energy nuclear physics, we understand the existence of a first order phase transition from vacuum to nuclear matter at a chemical potential of about 930 MeV. Once you add electromagnetism, it makes nuclei, and these nuclei exist for about 8 MeV in chemical potential. And when the chemical potential exceeds the neutron mass, then in addition to nuclei, you have a gas of neutrons, which we think will be in a superfluid state because neutron interactions are attractive at the Fermi surface. And at some point, the nuclei disappear, and you have a phase of matter that is what we call nuclear matter, which is neutron rich because the conditions of beta equilibrium and charge neutrality favor a very asymmetric state of matter. And there is now reason to believe that their observations are suggesting that there also must be a strongly coupled phase of matter, and it's likely very relativistic when you get up to chemical potentials of order 2 GeV. And I will discuss this in greater detail in just a few minutes. And at asymptotic densities, we know perturbative QCD again begins to work. And we also know that color superconductivity is a very important aspect of understanding phases at these very high density. What we are hoping is for neutron stars to provide information about this very interesting region of the phase diagram between 1 and 2 GeV in chemical potential. And what I'm also showing you here is what these chemical potentials correspond to in terms of density. So you can see that the density range from about 10 to the 14 to about few times 10 to the 15 is what is accessed in neutron stars. And this can be treated at low densities for chemical potentials less than about a GeV using a description based on nucleons as the only active degrees of freedom and interactions between them defined by a low energy effective field theory. And at intermediate densities, we have to rely on observations to learn what the phases of matter there may be. Based on our current understanding, this is what a neutron star looks like to a theorist. Typical neutron stars have masses of about 1.4 solar masses, and their radii are somewhere between 12 plus or minus 2 kilometers, and I will talk a little bit about radius measurements shortly. In the outer regions, the outer few hundred meters, you have a crust, which is a solid. It's a Coulomb solid at low temperature. It's got relativistic electrons, but is in other ways very similar to ordinary matter here on Earth. The inner crust is already quite exotic because the inner crust is composed of nuclei, electrons, and as I mentioned earlier, because the chemical potential is larger than the neutron mass, you also have free neutrons that are expected to be in a superfluid state. The outer core is a very interesting part of the neutron star. It's expected to be a liquid composed of neutrons, protons, electrons, and muons. And the description in terms of nucleons, we think, breaks down when the distance that separates nucleons becomes comparable to the size of the nucleon. And that happens at around twice nuclear saturation density, or in these units, around 5 to 6 times 10 to the 14 grams per centimeter cube. And there is this region which I label as quark-hadron transition. It really is just a placeholder for a realistic understanding of a strongly coupled phase that is probably characterized by a high speed of sound. What this is, we are, many of us are actively working on it, but we don't have a clear picture of what this phase of matter could be. And the big question is there any part of the neutron star where quarks are weakly coupled quarks, may be a good starting point to describe its properties. And the evidence for that seems quite unlikely. So even if quarks do appear, the question would be, whether they appear in a color superconducting state or in some other phase where the correlations between quarks remain very important. So let me start by just giving you, reminding you of the fact that neutron star observations have been leading the way in this field. We now have compelling evidence, almost for 10 years, that massive neutron stars with masses greater than 2 solar masses exist in nature. And these are observations of neutron star binaries, typically containing a neutron star and a companion. The companion is a white dwarf in some cases. And the beautiful measurements that have been made available through radio astronomy, pulsar timing, is that we are able to look at post Newtonian effects on the orbital period, in particular measure effects like called Shapiro delay, which allows us to measure the individual masses of the two objects in the binary. And this analysis has led to measurements that suggest that the neutron star mass in at least 3 of these systems is greater than 2 solar masses. Very recently, there is an analysis which is not quite as gold-plated as the radio measurements of neutron star binaries, where all you have to put your faith in is general relativity to extract the masses. There are other models of binaries, especially neutron stars in black widow systems, where a neutron star accretes a large amount of mass from a companion. There are suggestions in the literature that one of these systems may be as heavy as 2.3 solar masses, but this is to be taken with a grain of salt because these are not quite as clean as the measurements based on just pulsar timing. But it opens up the possibility that neutron star maximum mass may be higher than 2 solar masses, maybe closer to 2.3 solar masses. Neutron star radii have been very difficult to measure. That's because the surface emission is complicated to model. We often don't know what the atmosphere of a neutron star is. And it becomes important to understand the neutron star atmosphere if you want to derive constraints on the neutron star radius just from something like emission that would be similar to a black body emission and hence sensitive to the surface area. What we have been able to measure through modeling although systematic errors remain a major problem, by looking at quiescent neutron stars, these are neutron stars that are not exhibiting any bursting behavior or any unusual temporal behavior in their surface X-ray emission. Studies of such systems usually favor neutron star radii in the range 10 to 13 kilometers. But this line of activity, this way of trying to extract neutron star radii has kind of hit a brick wall because of poorly understood systematics. This led in recent years to find alternative ways in which one can measure the compactness of a neutron star. And NICER, which is a X-ray instrument on the space station, it has been looking at a few neutron stars very intensely, collecting large amounts of data on the evolution of X-ray flux from the surface of the neutron star. And because these neutron stars have hot spots on them, they could potentially have more than one hotspot. And the way we see this is by looking at the temporal variation of the X-ray luminosity, which is shown here in this plot. When the spot is in your field of sight, you get a high luminosity. When it gets behind the neutron star, the amount of radiation that you see from the hotspot when it's behind depends on the space-time geometry, because these objects are so compact that light bending plays a very important role in determining the rotational pulse profiles that we see from these systems. And by modeling these hotspots and looking at the data, one can constrain the compactness of such objects. Again, there's some amount of modeling that goes into the extraction of neutron star radii from this, but this is expected to have smaller systematic errors compared to extracting radii from just quiescent emission from neutron stars that I mentioned earlier. What we find is that there are two objects that have been studied, an object whose mass is expected to be very typical with 1.4 solar masses, and the radius, 1 sigma radius region for this object is between 12 and 14 kilometers. And most interestingly, they also were able to study a neutron star with a very high mass, pulsar J0740, whose mass is expected to be slightly above 2 solar masses. And in this case, two separate analyses suggest that the neutron star radius is likely greater than about 12 kilometers. Again, 1 sigma errors here. And one study finds that it can be as large as 16, and another study that makes some reasonable assumptions about the range of radii possible suggests that this could be somewhere between 11.5 and 14 kilometers. The most accurate way in which we can measure neutron star properties will turn out to be gravitational wave physics. And the reason for that is what I'm about to describe here. Gravitational waves from the very first neutron star merger already told us that some source parameters, such as the chirp mass, which is a specific combination of the masses of the two neutron stars, can be measured very, very accurately. The ratio of the masses, not as accurately, but typically, the expectation is that individual masses of neutron stars involved in a neutron star merger can be measured at the 10% level. And that's shown here. The individual masses of these two neutron stars that were involved in GW 170817 have been measured to about 10% accuracy. And these are pretty typical masses one would expect from the neutron star population that we see here in our own galaxy. What's interesting is that it's been realized for more than a decade that we can also measure the size of neutron stars using gravitational waves. And I'm sure you've heard about this many times. The basic idea is that there is the tidal forces between the two neutron stars deform them, and this deformation produces a quadrupole moment on the neutron star. And the amount of quadrupole moment that you can produce for a given tidal field is proportional to the tidal deformability of the neutron star. The tidal deformability of the neutron star is an intrinsic property of the neutron star. And it turns out that this intrinsic property of the neutron star is quite sensitive to the radius, and it can be measured through gravitational waves. So what happens when these neutron stars merge, this induced quadrupole moment speeds up the orbital evolution. Basically, you're taking orbital energy and putting it into an internal excitation of the neutron star by deforming it. And so that takes away energy from rotation and speeds up the rotational evolution of the neutron star. So this change in rotational phase can be calculated using general relativity, and one finds that this rotational phase is related to the dimensionless parameter called the tidal deformability of the combined system. And the tidal deformability of the combined system is some linear combination of the two objects. It's weighted by the masses, but the important fact is that it's a very sensitive function of the radius. It's proportional to the distribution of matter inside the neutron star through what's known as the tidal Love number, denoted by K2, and it's proportional to the fifth power of the neutron star radius. So if you can measure the tidal deformability, you get a very good constraint on the radius. So a 10% measurement of the tidal deformability will give you a 2% or even better measurement of the neutron star radius. That's something to keep in mind. And a great many groups, including LIGO, Virgo collaboration, have analyzed the data from GW 170817, and the constraints that you derive from GW 170817 suggest that the neutron star radius should be less than 13 kilometers. They typically favor radius in the range of about 11 kilometers, and the region with radius greater than 13 kilometers is usually excluded at greater than 90% confidence level. And again, one can also derive a lower bound on the neutron star radius by using the fact that a 2 solar mass neutron star exists. And for a 2 solar mass neutron star to exist, the radius has to be greater than a certain value. And that can be just derived from general relativity and causality. Why are these measurements important? We all, this community knows that there is a direct relationship between the equation of state and neutron star structure. And if one has the pressure as a function of energy density, one can solve the hydrostatic equilibrium equations in general relativity and get a unique relationship between mass and radius of neutron stars. And different behaviors lead to different mass radius curves. And what I'm showing here is this correlation between the behavior of pressure as a function of energy density and its predictions for the mass radius curve. One important feature that I can highlight is that if, for example, we find the radius of neutron stars to be small, of the order of, say, 11 kilometers or so, and we also find evidence for very large maximum masses in greater than 2 solar masses, then that would require a behavior similar to what's shown in this cartoon yellow curve, showing that there must be some region in the neutron star where you make a rapid transition from low pressure, which is required to make a small radius, to high pressure, which is required to make a large maximum mass. What we know about the equation of state of dense nuclear matter, again, this is a simple illustration of what we know. Around 10 to the 14 grams per centimeter is when you make the transition from the neutron star crust to the core. And there are some, important points here. Around 10 to the 6 grams per centimeter cube, you have relativistic electrons that dominate the pressure. And then around 10 times 10 to the 11 grams, that's when neutrons drip out of nuclei and they contribute to the pressure. And eventually at this density of 10 to the 14 grams per centimeter cube, you have neutron-rich matter where the pressure is dominated by nuclear interactions and by the nucleon degeneracy. I also mentioned that there's a region of this region of the density where we can calculate using traditional methods. Traditional methods, I will describe them in more detail, essentially rely on a non-relativistic treatment of nucleons interacting through 2 and 3 body potentials. And this region we can currently calculate, calculate meaning that we can estimate errors. And there's a very interesting region above 2 times 10 to the 14 or 3 times 10 to the 14 grams per centimeter cube, where we don't have tools to calculate, but there's a lot of interesting phases that are possible. And one of the motivations for studying neutron star observations is to see if we can tease out some of the properties of this region, which we can't currently directly calculate. The other interesting feature that's worth noting is that the radius of a typical neutron star of 1.4 solar masses is quite sensitive to this region of density where nuclear interactions are important. And in contrast, if you want to directly calculate what the maximum mass of a neutron star is from theory, that would be much more challenging because that is very sensitive to properties of matter at densities where reliable calculations are not currently present. So just a few words about traditional calculations of dense neutron-rich matter. And the idea here is that, and this has been a program that's ongoing for more than 20 years. The basic idea is that you have a non-relativistic Hamiltonian where nucleons interact with 2 and 3 nucleon potentials. And the 2 nucleon potential, we know a great deal about it from nucleon-nucleon scattering. And at short distances, we expect the potential to be repulsive. We expect the potential to be attractive at intermediate and large distances. And this is fairly well constrained. So any model for the 2 nucleon potential that you develop is usually very strongly constrained by data. The 3 nucleon potential, less so, but as I will describe, interesting developments in chiral effective field theory have provided some new insights about this as well. Once you have a Hamiltonian, there are fairly sophisticated quantum many-body methods, quantum Monte Carlo, many-body perturbation theory, Green's function. So there's a whole array of methods that can deal with these Hamiltonians. And one of the things we've learned is that the uncertainty associated with the equation of state as it stands now is really dominated by our uncertain knowledge of the Hamiltonian, not so much the many-body method. In the last 10 years, there's been a real change in the way we've been doing calculations of nuclear matter. And that's largely been due to the fact that we have a modern theory of nuclear forces, which is inspired by effective field theory ideas. And the effective field theory ideas are rooted in the observation that there's a separation of scales involved in the nuclear force. The heavy mesons that are responsible for the short distance interactions are much heavier than the pion. And so the separation allows one to build a nuclear Hamiltonian in powers of the momentum over the breakdown scale of this theory. And the breakdown scale of this theory is associated with the momenta at which details associated with the short distance force become important. But this effective field theory gives us a Hamiltonian as a string of operators, and at lowest order, all you have is a contact interaction who's with a low energy constant that needs to be fit to data and 1 pion exchange. And if you just use that very simple leading order calculation, you can make any prediction you want, and there would be an error associated with the fact that you've left out all of the higher order contributions. And so this program to calculate order by order in this Hamiltonian provides us 2 very useful insights. One is that it organizes 2 and 3 body forces systematically, and it tells you that many body forces appear at higher order, which means that there really is a hierarchy. And more importantly, it tells us when this method breaks down, when this expansion in terms of Q over lambda, where Q can be thought of as the Fermi momentum and lambda is expected to be about 600 MeV, is the breakdown scale of the theory. Before I show you the results, there are some things about chiral EFT that is actively being studied. It's not a perfect EFT. It has some very good features, but it has also some obstacles that people are actively working on. The good news is that we finally have a scheme to estimate errors and understand where description in terms of nucleons only breaks down. And it also provides very strong connection between 2 and 3 body forces. What's not so great about the EFT is that for neutron star applications is that the expansion parameter is about a third, gets larger with density, and it's not very small. So one has to be very careful to understand the truncation errors. And more work is needed to understand convergence and error estimates. I will show you some results, so please keep this in mind when I discuss these results. And what is highly controversial and tends to create some amount of pause in thinking about this as an effective field theory is that the regulator artifacts associated with the cutoff that one uses in calculations needs to be better understood. And the cutoff in current calculations in all of these calculations can only be varied over a relatively small range because of some technical issues associated with the existence of deeply bound states. So keep this in mind as we move forward and I discuss these results. So what a large number of groups, starting with pioneering work that Kai Hiebler and Achim Schwenk did in 2009, have begun to use EFT potentials to calculate errors associated with the equation of state. And what this plot here shows on the right-hand side is the neutron matter calculated over a density range from about half nuclear saturation density to about twice saturation density. And the different bands are obtained by using different orders in the EFT Hamiltonian. And the expectation is that these bands should overlap and that the band should get smaller as you go to higher order in the EFT expansion. And you see both of those tendencies, and it looks like EFT-based calculations of dense nuclear matter converges up to about twice nuclear density. And what I want to do is now look at what this implies for neutron stars. So again, going back to this equation of state, the microscopic calculations now are giving us an estimate of what the neutron star pressure uncertainty would be in this density interval, which is very important for the structure of neutron stars. And at nuclear density, these calculations predict a pressure of 3 MeV with a relatively small error. This is because the EFT appears to be fairly robust at these densities. But as you go to higher densities, around twice nuclear density, you see that this error begins to grow. And the question I am going to now address is, given this measurement, what can we say about neutron stars, even though we don't have reliable calculations in this interesting region? So the first thing we can notice is that there is a causality bound on how quickly the pressure can rise. The speed of sound, which is really just a measure of the rate at which pressure increases with energy density, is bounded. So that means that the pressure cannot exceed the region reached by just choosing an equation of state with the speed of sound equal to the speed of light. So there's an upper bound on the pressure at any given energy density, given this data point here. There's also a lower bound on the pressure because the pressure must be adequate to produce a 2 solar mass neutron star. So there's also a lower bound on the pressure, which is much more complicated than the simple straight line here illustrates. But there is a lower bound on the pressure due to the fact that the neutron star, you should be able to construct a neutron star starting with an equation of state at low density that can make a 2 solar mass neutron star. Just a brief word about speed of sound. Speed of sound is a very efficient way of parameterizing the high density equation of state in the neutron star inner core. For one thing, it's once you divide it by the speed of light, it's just a dimensionless number. It can only vary between 0 and 1. And it's also related to the baryon number susceptibility. So rather than talk about pressure and energy density, it's much more convenient and physically motivated to simply parameterize the equation of state at higher density in terms of the speed of sound. So using the speed of sound parameterization, what one can do is derive robust bounds on the neutron star radius. So this plot on the right-hand side is showing something familiar to us, which is the mass radius curve. And if I only use information about dense matter up to twice nuclear density, then I'm unable to construct neutron stars that are observed in nature with masses around 1.4 solar masses, but I can reach neutron star masses of about a solar mass. And so I need to extrapolate to high densities. And if I use an extremal scheme in which the speed of sound is set equal to the speed of light, then I explore the stiffest possible equation of state possible. And that gives me an upper bound on the neutron star radius. And these bands now depict the 1 sigma and 2 sigma predictions for the upper bound on the neutron star radius of any mass neutron star. It turns out that one can also derive a lower bound. This has not been proven, but it's a conjecture that's been borne out by all calculations. The smallest radius neutron star that you can create is one in which you have a very strong first order phase transition at twice nuclear density in this case, and then a very stiff equation of state with the speed of sound equal to the speed of light at the highest densities to ensure that you can make a 2 solar mass neutron star. So given information at around nuclear density or twice nuclear density, we can derive model independent bounds on the range of radii possible. And this will improve if we discover a neutron star with a higher maximum mass. I mean, there seems to be now suggestions that there could be a 2.3 solar mass neutron star, but if you had, for example, a 2.6 solar mass discovered, then that would be very restricting on the range of radii possible for any neutron star, given the low density constraints. So what we're hoping to do is improve the calculations of the low density part, have observations to give us inferences on both the maximum mass and on the radius, and see if all of this fits in a consistent picture. This seems very consistent with GW 1708 observations. So this is the current expectation for the range of radii from GW 1708-17. So this is a very clean gravitational wave measurement. The X-ray measurements from NICER suggest slightly higher radii, and this is a 1 sigma measurement, and again, a 1 sigma measurement that I mentioned earlier for the 2 solar mass coming from NICER is also shown here. So what's interesting is to ask the following question, if we improve our calculations in this interval 1 to 2 times nuclear density, how much does the radius predictions improve? So here I'm plotting the radius of a 1.4 solar mass neutron star as a function of the density up to which we can perform reliable calculations with error bars. On the left plot, I am going to assume that the speed of sound is only bounded by the speed of light, which is the most conservative approximation one can make. And you can see that as you're able to describe matter between 1 and 2 times nuclear density, the upper bound shown by the orange band and the lower bounds shown by different curves based on different maximum masses begin to converge, and the radius range allowed for neutron stars shrinks very rapidly as you improve calculations in this density interval. If the speed of sound doesn't exceed 1/3, because of reasons that has been conjectured in the literature, then you have a much tighter bound on the neutron star radius. So if, in fact, the speed of sound in QCD doesn't exceed 1/3, then knowing the equation of state, even at 1.5 times nuclear density, already puts very strong constraints on the neutron star radius. In this case, it would say that the neutron star radius would have to be between 12 and 13 kilometers, maybe even between 12.5 and 13 kilometers for it to be viable. And you can already see that there's a little bit of tension here because GW 1708-17 requires the radius of the star to be less than 13 kilometers. So these are, again, hints that maybe C squared of 1/3 is violated at finite chemical potential. So this is what one of the insights we've derived is that if you want to accommodate a large maximum mass and neutron matter calculations, which suggest that the speed of sound is small at low density, then neutron stars require a region of density where the pressure increases very rapidly. And this would correspond to a speed of sound that increases very rapidly. So we can safely conclude that a smooth transition from low density to high density, where perturbative QCD requires this to be about 1/3, can be ruled out. And there must be some region where it probably exceeds 1/3. By how much it exceeds 1/3 is not yet constrained by observations. There are many scenarios currently possible. You could also have a strong first order phase transition where the speed of sound increases very rapidly, and then the first order phase transition would create a region where the speed of sound would be 0 over a finite density interval. So since many of you work at the finite temperature and heavy ion collisions, I thought this is an interesting analogy. If you look at the speed of sound calculated using lattice and also using models such as the Hadron resonance gas model, you see interesting behavior in this critical region where the speed of sound first decreases and then increases as you transition from a region which can be described in using hadrons to a region where some sort of strongly interacting quarks intervene, and then eventually you approach the perturbative limit at very high temperature. At lower density, this is not a real calculation, but this is a cartoon based on calculations of the speed of sound in chiral perturbation theory and the expectation from Hadron resonance gas model, is that we expect a similar non-monotonic behavior. You don't exceed 1/3, but you see a region where pions dominate the energy density, and the lack of heavier degrees of freedom ensure that the speed of sound increases rapidly. And then you have heavier resonances begin to play a role, which decrease the speed of sound. So there may be an analogy here between what we are seeing from neutron star observations and what is expected in hot QCD. So one of the insights is, I think, what's going on at finite chemical potential and 0 temperature. This is what I suggest is a minimal scenario. At low densities, we know that chiral effective field theory and nucleon-nucleon interactions studied in the laboratory suggest an increase in the speed of sound because of the short-range repulsion between nucleons and three-body forces. And there's a region where the speed of sound is increasing very rapidly. It cannot be described in an effective field theory. And we think that a reliable description here will require some sort of strongly coupled matter where there is no small expansion parameter. Maybe it is a region where quarks are strongly coupled, and they could be in the form of quark-ionic matter, where quark-ionic here just implies that there are baryons at the Fermi surface, and these baryons at the Fermi surface continue to experience these strong repulsive interactions that contribute to the pressure. And this turnover could have something to do with the appearance of strangeness or with deconfinement, where these correlations begin to disappear. And we also expect a region where color superconductivity could play a role in determining the density dependence of the speed of sound. Eventually, the speed of sound will be determined by perturbative QCD, and Alexei Kurkela and his collaborators have shown that even though perturbative QCD only applies at very high densities, integral constraints derived from perturbative QCD can actually provide useful information on the equation of state and the speed of sound, even at lower densities that may be relevant for neutron stars. So there's guidance from PQCD on the evolution of the speed of sound in this intermediate region. And one is hoping that heavy ion experiments will also tell us something interesting about the speed of sound in this region. Okay, so it looks like I am going slower than expected, so I am going to speed up a little bit. That concludes the discussion of the equation of state. I'm going to briefly mention a few things about accreting neutron stars. and how they may be laboratories, low temperature laboratories for studying thermal properties. Accreting neutron stars are interesting because they are objects where accretion from a companion fills a accretion disk. And this accretion disk is stable for some periods of time, and then it becomes unstable. And when it is unstable, all of the matter in the accretion disk pours onto the neutron star. And when that occurs, you see X-ray observers see a phenomenon known as accretion outbursts, where you see a very high intensity of X-rays being emitted from this binary system. And once all the matter from the accretion disk, a large fraction of the matter from the accretion disk has been deposited onto the neutron star, the accretion disk becomes stable and it begins to grow from the matter that's coming in from the companion. And during this phase where the accretion disk is growing stably, matter is not accreting onto the neutron star, and this can be seen in the X-ray emission from the neutron star. So you go from a highly variable X-ray emission state during accretion to thermal emission from the neutron star with very small variability when the neutron star becomes quiescent. During this phase where you are accreting matter, there are nuclear reactions that can heat the star. And what one sees after accretion stops is this relaxation of the heated neutron star. So essentially what we currently understand about accretion onto neutron stars is that accretion releases about 2 MeV of energy in the neutron star crust, deep inside the neutron star crust, where the density is about 10 to the 10, 10 to the 11 grams per centimeter cube. And this heat that is deposited during accretion must eventually escape from the neutron star. And we've seen several of these sources. We have a total of 7 neutron stars that do this sort of heating and cooling cycles. And what we can deduce from all of these observations is, while there are important differences in the cooling curves post-accretion, the time scale associated with relaxation, which is this time scale of about 1,000 days, seems to be consistent across all of these different sources. And so that led to developing a theory for thermal relaxation of these accreting neutron stars. So from a microscopic point of view, if you want to understand what is the time scale for thermal relaxation, you can relate the time scale to the properties of the outer regions of the neutron star. You can relate it to the crust heat capacity, to the crust thickness, and to the thermal conductivity. And what one observes is that the timescale of 1,000 days is actually short compared to what one expects for matter at these high densities. And for having a short timescale, you require 2 things. You require a small heat capacity, and you require a large thermal conductivity. And neither of those will be satisfied if you have a very simple liquid or if you have a gas. So that's already pointing to some very interesting direct observational constraints on the state of matter in the outer regions of the neutron star. So if one needs to calculate the properties of the outer regions of the neutron star, especially the region where the heat is being deposited, which is the inner crust of the neutron star, one needs a theory at low temperature of the excitations of a superfluid of neutrons and a lattice of very heavy nuclei. What one finds is that really there are 3 degrees of freedom that are relevant: the relativistic electrons, the phonons of the lattice, and the phonons of the superfluid. And it's very nice that you can have an effective field theory with a clear separation of scales and very well-defined low energy degrees of freedom to calculate all these properties. And there are some interesting properties, like, for example, the superfluid phonons tend to mix with the phonons of the lattice, and that really limits their mean free path and their contribution to thermal conductivity. There are lots of very interesting aspects of the thermal and transport properties of the crust, but the good news is we can make reliable calculations of both the thermal conductivity and the heat capacity. And these calculations are very compatible with the cooling timescales that we observe. So this, to me, provides very strong observational evidence for the existence of both a solid made of ions, which is immersed in a superfluid made of neutrons. Maybe I will skip over this because I am going to run out of time. Just a minute. And talk a little bit about.
Sanjay.
Yes.
There is a question in the chat that is relevant to what you talked about, the thermal relaxation. And this is a question from Krishna. And the question is regarding thermal relaxation of a neutron star that is cooling after it was heated by accretion. Shouldn't the C sub V that enters be the heat capacity of the entire star? Why does only the CV of the crust enter the estimate? So that is a question.
Right. So that's because it's only the specific heat of the region where you have thermal gradients that enters the calculation. The regions where the specific heat, the core is isothermal and there are no thermal gradients in the core. So that's why the specific heat of the core doesn't enter the thermal relaxation.
Yeah. Does the heating from accretion heat up only the crust, or does the heating?
Yes.
It doesn't heat up the core?
It heats up the crust, and the heat from the crust is transported to the core. But the core has a very high thermal conductivity, so yeah.
Okay, so then I guess what I was curious about is the part you skipped, which is how can you constrain the CV of the entire star? But okay, why don't you do it the way you were planning and take that as a question for the end?
Yeah, I'll take a question about heat capacity of the core at the end. Okay.
Consider that question asked, but for the end.
Thank you for that question. Okay. What I'm going to now do is basically talk about the two other topics, which I think will give you a flavor of where the field is going, is the realization that upgrades to current detectors, gravitational wave detectors, and next generation detectors will give us measurements of neutron stars that are going to be very constraining for the equational state. The two detectors that are under consideration are that are going to be able to provide lots of neutron star measurements are Cosmic Explorer in the United States and Einstein Telescope in Europe. These are really going to be neutron star machines. LIGO, advanced LIGO is really a black hole machine. These will detect 300,000 neutron star mergers a year and about 100,000 black hole mergers a year. And the sensitivity curves for the various detectors are shown here. And you can see the Cosmic Explorer and Einstein Telescope really improving by about a factor of 10, the sensitivity in the region from about 100 hertz to 1,000 hertz. There are also efforts in Australia to build a detector which will be sensitive to the high frequency parts of the neutron star merger. And that would have useful information about post-merger dynamics, which I will mention in a minute. Sticking with in-spirals, about 100 binary neutron star mergers every year in this era of Cosmic Explorer will have a signal-to-noise ratio of greater than 100. The signal-to-noise ratio of GW170817 was about 30-something. So, and 5 of these every year will have a signal-to-noise ratio greater than 300. So if you have a signal-to-noise ratio for a binary neutron star merger greater than 300 kilometers, then various studies have shown that the tidal deformability of the neutron star can be measured very accurately, and the radius of the neutron stars involved in the merger can be extracted at the 0.1 kilometer level. And that would be, that's what I would say is the precision era for neutron star studies. They also measure the high frequency components of the post-merger phase, and that will probe the oscillation modes of the neutron star. So this is a really beautiful plot that was taken from the Horizon study for the Cosmic Explorer, basically showing the number of events detected every year as a function of distance from the Earth. You can see, typically one expects 1 or 2 events in this region to about redshift of 0.1, GW 170817, very close by event at 40 megaparsecs as shown here. And then as you get to a redshift of order 1, you start seeing a very large number of neutron stars, and these neutron stars are far away. It's very hard to measure the properties of these neutron stars accurately, but you will have a population of neutron star masses that will be very useful for other studies that we would like to do with compact objects. Neutron star merger dynamics has actually a lot in common with relativistic heavy ions. There are important distinctions, but I like to think of these as general relativistic very heavy ion collisions with an energy of about 100 MeV per nucleon. And there are interesting phases of this merger which are distinct. The in spiral that I talked about is clean in the sense that it only depends on the properties of the neutron star, such as its mass and its tidal deformability. The merger itself is violent. It has neutron star oscillations, hydrodynamics, and the transport properties beginning to play a role. And then the post-merger evolution has likely a gamma ray burst associated with it. So there's some interesting plasma astrophysics associated with creating these jets. And also there is the nucleosynthesis that ejects very large mass of radioactive material that power a phenomenon known as kilonova, which has been studied in great detail. What's interesting about post-merger evolution is that it has, it's complex, but it relies very heavily on the high density, high temperature physics of the QCD phase diagram between 2 and 6 times nuclear density, reaching temperatures of order, say, 30 to 50 MeV. And this can provide, eventually this will be able to provide access to this part of the phase diagram under equilibrium conditions. Even though this process is violent, it's still slow compared to strong interaction timescale. So the matter that evolves here is very close to equilibrium. And it could also be quite close to weak interaction equilibrium because of the high temperatures achieved. We know that the basic paradigm works because the observations already confirm expectations of the simple simulations we can perform. There's a gravitational wave followed by a gamma ray burst, followed by an afterglow and a kilonova. So it's remarkable that, this very complex phenomena, even with the simplest models that we have, gets the broad brush pictures right. So this gives us hope that, with more effort and more data, we can extract some useful physics. What's interesting about this is that the amount of matter that you eject can be studied from electromagnetic observations. And the composition of this matter can also be examined with electromagnetic observations. And these are observations of the kilonova. And it looks like there are really 2 distinct types of material that is ejected from a neutron star merger. One that is unaffected by the neutrinos that are produced inside this very dense hot object, and that tends to be very neutron rich, and that's where most of the heavy elements are made. And another component that is processed by the neutrinos that are emitted from the merging neutron star, and that tends to be less neutron rich, and that produces a different set of nuclei that are not as heavy. So it's possible to combine gravitational waves and electromagnetic observations to not only study merger dynamics, but also study how much matter is ejected, what's the composition of matter, and that really is going to be a very active area of research once we have more data and more faithful simulations. Studies also show that astroseismology is something that is an active field that can be measured with next generation gravitational waves. And what one is showing here is that there are clear features in the frequency power spectrum, which are sensitive to the equation of state and oscillation modes of the neutron star. So what will this look like? Eventually, we will have a mass radius measurement coming from a few years of operation of Cosmic Explorer with measurements that are better than 10% on the neutron star radius. So it will take a short amount of time once these detectors are in operation to constrain the neutron star radius, and that's basically this mock data that I'm showing you suggests that. But perhaps what will be really interesting is that these measurements will also give you a bound on the maximum mass of the neutron star, coming from the fact that we will know how long it takes to make a black hole in these mergers, and we will have a fairly good understanding of the maximum mass of neutron stars. We have to keep an open mind for surprises. Using standard nuclear physics, there is only one class of neutron stars we can make with which radii that cannot vary by very large amounts. And what I'm showing here is measurements that could point to physics that's beyond the standard model, or physics that involves multiple phases in QCD that may be metastable, and this would ultimately be one of the most interesting discoveries one can make. I see that I have come to the end of my time, so I'm going to maybe just stop here, go to my conclusions, and then take questions, see if we have time to say something about dark matter later on. So what I am going to now conclude, and then I'll take questions, is that the speed of sound in the neutron star, there's evidence for it to rise rapidly, and it probably implies the existence of some phase of matter which is relativistic and strongly coupled. There are many suggestions, and we'd like to know which one of those suggestions is correct. Thermal relaxation in accreting neutron stars, I think, provides evidence for what we thought should be in the outer regions of the neutron star, which is a solid crust with a superfluid neutron fluid. The first observations of neutron star merger exceeded our expectations. I think the basic paradigm of what to expect was borne out. But Cosmic Explorer and even upgrades to the current LIGO will provide much more useful measurements for constraining the equation of state. And interpreting multi-messenger observations, I think, is an exciting area of research where heavy ion physics, nuclear physics, and numerical relativity can come together to understand these very heavy ion collisions in space. And there's really good prospect for discovery because this is largely uncharted territory. I didn't have time to tell you anything about dark matter, but I'm happy to bring that up in the question hour if there are questions. Thank you very much for your attention.
Okay, thank you very much. So, but you skipped the dark matter part, but just only a few words to summarize the idea or some finding, or maybe before the question.
Okay, let me try to do that in 1 minute or a couple of minutes. So in principle, if you have dark matter in neutron stars, it could affect neutron star properties. That's the bottom line. And the question then is, why are neutron stars good places to look for dark matter? There are three reasons why neutron stars can contain dark matter. The first reason is that at high densities, you could have processes that violate baryon number or lepton number that are very rare, that can populate the neutron star during its lifetime. So neutron stars live about 10 to the 10 years or longer. And during this time, even a very slow process can produce some amount of dark matter component in neutron stars. If dark matter has a mass less than a GeV, then because neutron stars are born at high temperature, and because high temperatures are also realized during a neutron star merger, you have two opportunities to make sub-GeV dark matter thermally. And what one finds is that one can make about 10 to the minus 4 solar masses of dark matter just using the thermal energy of the supernova. And the most robust way in which you can collect dark matter in the neutron star is because dark matter will be present in the ambient regions around the neutron star, and the gravity of the neutron star will accrete this dark matter. But the amount of dark matter that you can get from accretion is very small. It's about 10 to the minus 15 solar masses in a giga-year for typical dark matter densities. So these are three ways in which one can get dark matter. One very simple example that illustrates why neutron stars can constrain dark matter scenarios is this suggestion by a few particle theorists to account for the neutron lifetime discrepancy. So the measurement of the neutron lifetime, which is a very basic quantity, using the bottle in which you're really counting neutrons, and the beam experiment in which you're really counting protons, those disagree. And the disagreement can be reconciled if you have a new channel for neutron decay in which you make some dark particle. My own feeling and the feeling of people who understand this field is that this is likely an experimental problem that's going to go away. But it motivates, in general, a scenario in which neutrons can decay into some exotic new state, which is dark. So the simplest model you can write down is one in which the neutron mixes with a dark partner, and the mixing angle, which measures the rate of this decay. If you want to fit the experiment, you need a mixing angle of 10 to the minus 9. But neutron stars live for a giga-year or longer, so you can probe mixing angles much smaller. So it'll take, most of the neutrons will be converted into these dark particles inside a neutron star, even if the mixing angle is only 10 to the minus 18 solar masses. Now, if that happens because you lose a lot of neutrons, the equation of state becomes soft. It turns out there's nothing you can do to make a 2 solar mass neutron star. So here's a simple observation of a 2 solar mass neutron star that basically says, unless this dark matter is also very strongly interacting and has a speed of sound close to the speed of light, it's unlikely to be able to explain a 2 solar mass neutron star. So this is one example that tells you you can start exploring dark sectors using neutron star observations.
Okay. Thank you very much. Okay, now let's go through the questions so we collected in the chat box. The first question is from RHIC. So he asks, there seems to be a 10 orders of magnitude jump in density between barium chemical potential 900 and 939 MeV. How should I think about this? This is about the very first part of the presentation.
Yeah.
This one.
Yeah.
So the baryon number susceptibility is, connected to the speed of sound. So if for a small change in chemical potential, you see a very large change in density, it means that the speed of sound is very small. So
that means this is basically the dissociation of nuclei into nucleons. This is first order phase transition with very large latent heat.
Exactly. But you see that at 930 MeV, the density is only 10 grams per centimeter cube because of the same reason that you mentioned, that you make nuclei and the nuclei have zero pressure and they're very heavy. So if you did not have any Coulomb interactions, then you would have this first order phase transition that you're talking about, which will make nuclear matter. And you see this large jump from 0 to 10 to the 14. But the fact that you have Coulomb interactions then spreads this first order phase transition over a much larger scale. So you have a big phase.
It really does change the order of the phase transition. It doesn't just move it around in a more higher dimensional space.
It moves it around a higher dimensional phase. It's still first order, but it's a mixed phase.
Okay, so it's like strangeness distillation in heavy ion collisions. Yeah. Okay. Right. Yeah.
Okay. Now the second question is about the tidal deformability. How well is the love number known? What observations and models can constrain it?
Yeah, so the love number depends on the distribution of matter inside the neutron star. So it's weakly dependent on the radius and the compactness of the neutron star. So it changes from equation of state to equation of state. but that change is relatively small, which means that if you want to measure the tidal deformability from observations, it's going to be tough. You will need, maybe with Cosmic Explorer, we can measure. You have several neutron star measurements over a mass range, and then you can extract the tidal deformability from these measurements. But again, you'll need to know the mass to very high accuracy to be able to do that.
But to turn it around, you don't need to know the lab number to use it for the radius determination.
Yes, that's right.
Okay,
so,
thank you.
The error induced in going from the tidal deformability to the radius is smaller than expected because the tidal number doesn't change very much from equation state to equation state.
Thank you.
Okay, now the question is closed, and then let's go to the next question. That was actually the question asked by Krishna, but Krishna reformulated the question in an official way. That is, please tell us how we can learn about the C sub V, the heat capacity of the entire star, not just the crust.
Right. Yeah, I seem to have, let me go to the slide.
I'm also confused about this point. So the accretion makes the the process is in the crust region essentially, right?
Right.
Yeah, it's a different process. He needs a different process to answer the question, which he skipped. So that's what I'm curious to see.
Okay, so the thermal relaxation of the crust is you heat the crust and you create a temperature gradient in the crust, and the gradient in temperature relaxes. So what you're doing in that calculation is basically solving heat diffusion in the crust. And anywhere the thermal gradient is 0, that doesn't enter the calculation of thermal transport. Now I'm going to answer the question that Krishna asked, which is, how do you measure the heat capacity? Okay, so let's take a very simple point of view. You have some source of heat, you provide that heat to the neutron star, and then you give the neutron star enough time to equilibrate that heat. And what happens here is that if you know the amount of heat that you've given the neutron star and you can measure the change in its temperature, then you can measure the heat capacity. So accretion clearly is doing this. So accretion heats part of the star, and some of that heat goes into the entire star over a longer time scale, not during the thermal relaxation time, but over a larger time scale. Now, what you know also is that the heat capacity of degenerate matter is linear in temperature. So if you use that assumption, you can relate the final temperature and the initial temperature to the heat capacity. Now, you don't know what the initial temperature was, so you can derive a lower limit on the heat capacity by just knowing the final temperature of the neutron star. So you have a non-equilibrium process that heats the star, you wait long enough, the heat is redistributed over the entire star, and now you're measuring the heat capacity of the entire star. So what you need is you need an experimental measurement of delta Q, the heat you provided, and that experimental measurement comes from the fact that you need to know how much heating is there per unit of accretion, and the duration of the heating. So that's given in this equation here. And you also need to know how much neutrino losses took away the heat. So delta Q can be calculated if you had the neutrino luminosity, the accretion rate, and the duration of the accretion. All of these can be measured in principle. In particular, you can calculate what the heating rate is by looking at the accretion, and you can measure over what period the neutron star accreted. So you know H dot and you know TH. And we have a few observations of this object called KS 1731. We know the surface temperature of this object. We know that it accreted for about 12 years. The accretion rate deduced from X-ray observations is about 10 to the 17 grams per second. And we know that it took about 8 years for it to relax. So you can now put all of this together and ask what is the inferred core temperature once it's relaxed. And the inferred core temperature depends sensitively on the outer regions of the neutron star. If the outer regions of the neutron star has very heavy elements, then you have an insulating region. So the surface temperature and the core temperature are related by this equation that are shown here. And if you have a light element atmosphere, then the core temperature and the surface temperature are closer together, and that's what's shown by the second equation. So you put all of this information together and you find that the amount of heat, and in this short time period, the neutrino losses are expected to be small for typical neutrino cooling. So you can ignore the neutrino losses compared to this 10 to the 43 ergs of heating that you're putting in. So this is how you estimate from observations how much heat was supplied to the neutron star. And because you have a measurement of the neutron star core temperature through this relation, now you have a lower bound on the neutron star heat capacity. So this lower bound on the neutron star heat capacity is shown here. So if the neutrino luminosity is very high, then most of the energy is lost through the through neutrino radiation, and you become very insensitive to the heat capacity from the observation. But if the neutrino luminosity is less than 10 to the 36, then you see that for neutrino luminosities of 10 to the 35 or below, you have a really good bound, a lower bound shown by the black curve here. And these different curves here basically depict different periods over which you assume the same phenomena has been going on in the neutron star. So this lower bound that you derive from looking at the surface temperature after the star has relaxed shows that the heat capacity should be greater than a few times 10 to the 36. And that's consistent with observation, but with calculations. It shows that just leptons, if all of the nucleons in the neutron star, assuming neutron stars had only nucleons, were paired, then you have a heat capacity as large as that's shown by the region that's labeled leptons.
That's the electrons, basically.
That's basically electrons and muons. That's the heat capacity in the orange region. Now, if you take very extreme case where you say 90% of the neutron star core is made of matter, where all the made of matter in which all the quarks are paired, there are no low energy degrees other than the Goldstone bosons in the CFL phase, then you get a heat capacity that's very small. So it excludes these scenarios that seem unlikely from the get-go, where 90% of the neutron star is made of equal numbers of up, down, and strange quarks in the CFL phase.
But if you had 1/3 of the star in quark matter, but that quark matter was some phase other than CFL, that's perfectly allowed.
That's perfectly allowed. So in fact,
so what's excluded is a very large fraction of the star in CFL.
Right.
Okay,
and,
that's great. So what are the prospects for other observations making this constraint more stringent?
Yeah. So if you,
I mean, on this star or other stars?
right. So what you'd like to see in such an object is a variation in the surface temperature in this quiescent phase over some period of time. So
Right.
for example, if you see this object for about 6 years and you see a change in temperature of 13%, then that's really interesting, because that would require, for one thing, that the neutrino luminosity was high, and it would require simultaneously that the specific heat was low. So this gray region that I'm pointing to with the mouse is the region that would be favored if you saw a 13% change in the surface temperature after this bout of heating and relaxation. So to see such a large change in the surface temperature, you both need a high neutrino luminosity, but you also need a low specific heat.
Yeah. Okay. Very cool. Thank you very much, and thanks for the great talk.
So probably this the heat capacity of the entire star depends on the mass of the neutron star. And so if more observations are collected for different mass neutron stars, then maybe more differential information could be available in the future. Yes.
Absolutely. So there's also a very interesting paradigm in neutron star cooling that I didn't get a chance to mention.
Mm-hmm.
So there is evidence for some neutron stars to cool very rapidly.
Mm-hmm.
There are two classes from a very naive neutron star cooling point of view. There seem to be two classes of neutron stars. Neutron stars that cool slowly, which are very compatible with our current understanding of neutrino processes. And then there are neutron stars that cool very rapidly at a rate which is compatible with what's in this field called as direct Erker reactions, involving beta decay of just either a single quark or a single nucleon. The only way we can distinguish these two classes is by saying that the slow coolers have to be light neutron stars. They have to have small mass, and the fast coolers must have high mass. If we are lucky enough to find the mass of neutron stars that are cooling fast and they are high, then it would fit in with the theoretical picture. But if that is not true, that would upset the entire picture. So, there are some real simple observations that can really test the basic paradigm of neutron star cooling.
And very challenging. Okay, so there is a hand from Nushu. So please go ahead.
Yeah, hi, Sanjay. I have a question on maybe just clarify. When you compare the speed of sound in hot QCD calculation, could you go to that slide? About this curve you draw by hand. Because maybe two parts. One is the QCD calculation, I think is at the mu b equal to 0. Is that right? And
yes.
Do we, in that environment, do we expect maybe before this? Yeah, before this slide. Right.
Yeah.
No, with your hand.
Yeah, I'm getting there. I know what you're talking about. Give me a minute.
Okay. Maybe two parts. One is, do we expect this your hand drawing curve at mu b equal to 0? Number one. Number two, is this curve really at final density really observed? In that you say
No. So this is zero density finite temperature. So
right.
The reason I showed this was to show that kind of an analogy between what we are expecting from neutron star observations and low density calculations, and what you are expecting and what can be calculated more reliably at finite temperature.
I see. What will happen if we have a density there in this lower temperature part? Do we know? I mean, because this is a region actually we could experimentally assess.
He has another plot which he talked about at length. This is his zero temperature plot.
Yeah, but
So
this is
so you're asking what happens when you have both density and temperature?
Yes, this is zero temperature. I also noticed.
Right.
And what happened, because we do experiment, we cannot create matter either zero temperature or zero density, right? So,
right. Yeah. So if you have baryons, if you have just a few baryons in this mix, I would say that the speed of sound would be lower. But if you have a large number of baryons, once you start filling the baryons so that the short-range repulsive interactions become important, then I would say the baryons would start adding to the sound speed. So if you have a high baryon density compared to the meson density, you would expect to see behavior that we are expecting in neutron stars. So it's a question of what dominates the energy density. Is it the baryons or is the mesons?
Well, Sanjay is emphasizing the analogy, but I must say that it is a bit confusing analogy because here entirely the speed of sound is below the conformal bound. And of course, this down peak is a remnant of the some second order phase transition. The crossover is similar to the cross to the second order phase transition, in which, of course, it goes down, or in the first order phase transition, it becomes 0. But if you see the dense situation, or it goes up above conformal bound, so maybe it is a genuine peak, but this is something that looks like a peak because of their down peak afterward. So I think that the complete analogy is not really the situation.
Yeah, this is not like all analogies. It's not perfect, but what I wanted to emphasize is there is a change in the nature of the degree of freedom that's playing a role, right? You know, the chiral perturbation theory was describing a bunch of pions, and these pions didn't have, I mean, you didn't have enough energy to access new states, and that's why the pressure rose. And if that persists in finite density, it would mean that, you know, nucleons must persist until very high density to see this rapid growth in speed of sound.
Thank you.
So is there any other question? Comment or? Yeah, actually, I have one small question. That is, so you show the chiral EFT and showing the result up to 2 times the saturation density, but what is actually the estimate, conservative estimate, up to what density the chiral EFT is trustable? So
Yeah,
that-
this is, so this is a question that can be answered only through calculations, right? So you have to do the calculation. You know that the breakdown scale is about 600 MeV. So you cannot use this when the Fermi momentum becomes about a 600 MeV. I mean, it absolutely is not a useful description at those densities. But whether it breaks down at nuclear density or whether it breaks down at twice nuclear density, that is something you have to find out by looking at the evolution of the truncation errors.
Mhm.
So
maybe,
if
maybe 2 is already a dangerous region. That's my impression.
say that again.
Maybe 2 is already in a bit dangerous region. No.
Yeah. So we are working. I mean, many people are working hard to find out what that statement really means quantitatively, right? What we'd like to do is, realistically, the Fermi momentum only changes by 25% when you go from nuclear density to twice nuclear density. So what is it? What is the small parameter we are expanding in? And the small parameter here is Fermi momentum over the breakdown scale. And the breakdown scale, let's say, is 600 MeV. At twice nuclear density, the Fermi momentum is close to 400 MeV. And and at nuclear density, the Fermi momentum is 330 MeV. Why should something really interesting happen when the Fermi momentum changes from 330 to 400? That is a fundamentally important question. And if you look at this evolution of the errors in an EFT calculation, again, there are many caveats, but if you look at the evolution of errors, there is really no sign that it's breaking badly in this interval.
So there is a comment from Thomas Schaeffer saying that the convergence does not mean it's converging to the right answer.
Absolutely, absolutely, yeah. That is certainly true. And I should also mention that there's no independent experimental confirmation of the predictions of chiral EFT for finite matter, but chiral EFT is used quite successfully in nuclear structure calculations.
Mhm.
So it's not tested directly, but it's tested indirectly.
Mhm. Okay, so is there any other question or comment or something? No? Okay, thank you very much for a great talk. There are interesting discussions and stimulating comments. So thank you very much.
Thank you very much.
for the
Bye-bye.
opportunity. Bye.
Thank you.
Thank you,
And
Sanjay.
Bye. Thanks. Bye.
Thank you all, and see you next week. Also,